Hello and welcome back. In example 2, we're going to bring back something that we learned many packets ago, which is the intermediate value theorem. We're going to use this intermediate value theorem and Rolle's theorem combined to help us show, in example 2, that the equation x cubed plus 3x plus 1 equals 0 has exactly one real solution. And the way we're going to do that is we're going to use the intermediate value theorem to show that there is at least one real solution to this equation. And then we're going to show, use the Rolle's theorem and a contradiction to show that there can't be any more than one real solution to this equation. So let's get started by first establishing that this function satisfies all of the conditions of both the intermediate value theorem, which requires that the function be continuous, and Rolle's theorem, which requires continuous on the closed interval and differentiable on the open interval, and then a start and an end function value that are the same. So we're going to start by writing up that at least the conditions of that are in common, or the conditions for the intermediate value theorem and Rolle's theorem are going to be met. And the reason we know that is because here we're going to take our function to be this polynomial on the left side of the equation. And since it's a polynomial, that polynomial is continuous and differentiable everywhere. All right, on the interval from negative infinity to infinity. Now, the first step is going to be use the intermediate value theorem, IVT for short, to show that there's at least one zero, to show that f has at least one zero. All right. Remember, the way we do this is we find an x value where the function is negative, we find another x value where the function is positive, and the intermediate value theorem would say that there's got to be some x value in between those two where the function is 0. Let's write up those x values, and this could differ based on whatever x values you find. So here I'm just going to use -1 and 0 as our two x values, because at -1 our function ends up being equal to -3, sorry. If you plug in -1 into the function, you end up getting -3, which is less than 0. And if you plug in 0 into the function, you get +1. Main thing is that that's positive. It's greater than 0. So, by the intermediate value theorem, there must be some x in the interval from -1 to 0 such that, you could use st if you wanted to here, f of x, and instead of there must be some x, you could say there exists an x, the backwards e, if you wanted to use some shorthand, such that f of x equals 0. In other words, we have a 0 of the function. So in other words, f has at least one 0. But there could be more than one, and we're asked to show that there is exactly one real solution. So we have to narrow it down, that it has to be exactly one. There can't be 2 or 3 or 4. It has to be exactly one. So here's where Rolle's theorem is going to come in. Now we're going to use Rolle's theorem to show that there can't be any more than one 0. So to show f has at most one 0 and no more. Now, the way we're going to do this is by a contradiction. We're going to say, suppose f had 2 zeros. Suppose that happened. What would have to be true? What would follow from that? Suppose there are 2 zeros. We'll call them A and B. And what it means for A and B to be zeros is that f of A is equal to 0 and f of B is equal to 0. So we can write f of A is equal to f of B, which is equal to 0. Okay, I'm going to put a little star by that statement. All right, well, if f of A is equal to f of B, well, now Rolle's theorem is going to kick in. It's going to say, aha, we've got two function values that are the same. So therefore, on the interval of x values in between, there's got to be some x value where the derivative at that x value is equal to 0. Rolle's theorem comes alive and says that there must be a c representing an x value, in the interval from a to b, at which the derivative is equal to 0. Okay, well, let's see if there's any problem with that. And there is, because f prime of x, the derivative, we can calculate. That's 3x squared plus 3. 3x squared plus 3. But that's positive. That's positive for all x. But this contradicts the fact that f prime of c has to be equal to 0. Rolle's theorem just said, look, if we've got f of a equal to f of b, then by Rolle's theorem, there has to be a c on the interval from a to b at which f prime of c is equal to 0. But that can't be the case because f prime is always positive. So something about our assumptions must have been wrong. So going back, it's the star that suppose there are zeros a and b. That supposition must be incorrect. Right? That was the hypothetical. Suppose we had this case where there are 2 zeros. Well, that leads to a contradiction. That leads to nonsense. And so there couldn't be 2 zeros. There can be at most 1 zero. So what we can write up is, this is a contradiction. So star lied to us. No, star is false. So f has at most 1 zero. Now that we've pinned it down, there's at least 1 zero and there's at most 1 zero, then that means that there is exactly 1 zero. Fix that h. F has exactly 1 zero. And so x cubed plus 3x plus 1 equals 0 has exactly one solution. Just enough room to write a celebratory box. There we have it. So just as an overview, we said, for example 2, if we're asked to show that this equation has exactly one real solution, we turn the equation, like solutions to an equation, into zeros of a function, right? Because those two are kind of correspond with each other. If you find a zero to a function, that gives you solutions to an equation, the related equation. And we set up to write the conditions of the intermediate value theorem and Rolle's theorem, saying that the function is continuous and differentiable everywhere, so it's going to satisfy the conditions of the intermediate value theorem and Rolle's theorem. And so then we used the intermediate value theorem to show that f had at least 1 zero by showing that there was an x value where the function was negative, another one where the function was positive. So by the intermediate value theorem, there must have been some x value inside this interval from -1 to 0 such that f of x is equal to 0. So this is pinning down a place where the function has to be 0. You can see in the picture here that between x equals -1 and x equals 0, there is a place where the function crosses the x-axis, and that's a 0 of the polynomial, or 0 of that polynomial function. So there visually is what we see. It's like -0.35, something around there. And but we're not finding exactly what that x value is. We're just saying that there has to be one x value that is a solution to the function equals 0. But at this point, all we have is that the intermediate value theorem says that there's at least one 0. There could be more, because you could maybe have other intervals where the function like dips back down and intersects the x-axis again. We don't know that at this point. But f has at least one 0. Then we use Rolle's theorem to show that if f has more than one 0, then we get this nonsense thing that happens. So suppose that there are two zeros, a and b. Well, then f of a would have to equal f of b, which is equal to 0. So by Rolle's theorem, there'd have to be a c in the interval from a to b, at which we have a horizontal tangent line at which f prime of c is equal to 0. But the problem is f prime is not equal to 0. It's always positive for all x. And so because of this contradiction, we know that there can't be two zeros, a and b. There has to be at most one 0. So there's at least one 0, and there's at most one 0, so there has to be exactly one 0. So therefore, our equation has exactly one solution, and there it is in the picture. Thanks so much for watching, and see you in the next video.